And you can either do it to match the actual equipment or personnel that are in the mine at the time, or you could use it to actually move air from one part of the mine where you don't need it to another part of the mine and drive optimization in that way. There's the potential for reduction in power consumption. And because we're in a northern climate in the winter, we actually have to heat our air that we pump into the mine, otherwise we'll end up freezing the shaft up. And we heat that air with natural gas, so there's an obvious, you reduce the volume of air, you reduce the volume of natural gas consumed. The economic justifications, we went through several different approaches to work out how much we can actually save on here, and the numbers you come up with are really huge. Potential energy savings of between 34 and 48%. There's a lot of opportunity, and this is why this is something that the mining industry is all over. And we're leading the way in that respect. So there's some challenges along to doing this. So the challenges, and you'll see where I'm going with this, it brings about what are the best practices in even starting a project like this. So the challenges are really, measurements are very difficult to perform. They're interactive. When you put more air on one level, you rob it from another level. A mine is always a continual construction site. Unlike regular plants, you build them, you run them. A mine, you're continually building for the whole of the ore body life. And then the fourth one, system response, is really affected by a whole lot of multiple factors, some of which you may not even know about. So it really is a multivariable control problem. And that being the case, you really should approach it in the same way that you would any other kind of control problem, where you approach it from a hierarchical fashion, where you start off in the bottom by putting in your actual measurements. You start off with simple control, and you could build more and more advanced controls on top of them. And then your return, your curve, the shape might look pretty different depending on what you're doing, but generally as you operate up further and further on this hierarchy of control, you get a better return. Unfortunately, robustness looks the other way around, and that's just a law of nature. You know, the more complex you make the system, the more things you need to make it work, the less chance that everything's going to work at the same time. So the robustness curve looks a little like that. And that really reaffirms the importance of when you do any kind of control project, and this is just an example of it, you really, if you don't build it in that kind of hierarchical fashion, you end up with something like this. And what this really represents on the left is you put in your measurements and straight away you slap your advanced control system on top of it. Okay? So your pyramid looks like this. And what it means that if everything you need to make it run up here, and in this case it would be fully dynamic ventilation demand, no problem, you're running in a very, very great area return. But you suffer one failure and you're forced to run down at this very, very low level of automation, which may even be manual. And so you miss the opportunity to you either really do very well or you do very badly. So with this thinking in mind, the way we built our ventilation on demand, we really built it and are running it in 3 stages. First stage is really just remote control of ventilation components. Now that name may not sound very, very fancy to people, but it really is. That in itself is quite a step forward for mining, is that you can sit on surface and adjust your ventilation components, so that's regulators and fans, and you can actually control that from surface. Right? That's a great start. Stage 2 we call mode-based control, where you have preset recipes, and depending on what's going on at the mine at the time, you select that recipe and it presets everything up to an optimized level. So shift change turns everything down because there's nothing happening underground. If you've just blasted, you need some areas, a lot of ventilation in one area to clear blast gases. So you set your ventilation up according to a set of recipes. And stage 3 is really dynamic, where you have a model of the mine, equivalent to what would be model-based process control. Really, you have a model of the mine, and based on where all your equipment is, and that's detected by the tracking system I showed you earlier, it dynamically adjusts the air in different portions of the mine to match that which is required by your personnel and your equipment. And this is just an example of it. We have air on a level underground would be controlled by a regulator, really a set of dampers at the end of the level that controls the amount of air through the level. And this is just a snapshot from our control system, where our ventilation control system where in real time now we have an actual airflow. We have modeled airflow that's based on the model. So in the absence of a physical measurement, we can run on the model. And then we have at the bottom here, if I can get this to work, but anyway, on the bottom of the display, you'll see there's a list of the equipment that currently has been detected in that area. And the system then adds up with knows the horsepower of the equipment, works out, well, for this much horsepower, this is much air I need, and calculates a demand. And now, depending on, we can now choose to operate on any of those levels. Okay, we can switch that to OMVD control, which in this example it is, and it's controlling the air to match dynamically the actual equipment that's detected in the area. And when the equipment moves out of the area, it'll delay, it'll time out, and then reduce ventilation automatically. We do a similar thing for auxiliary fans underground. When we started this project, we did not install variable speed drives on any of the underground fans. We weren't sure whether we were going to be able to utilize that, but we've actually proven that, we can, certainly in our workshops, we know exactly what equipment, when equipment drives into any underground workshops, with our tracking system, we know exactly when it's arrived, we know if the engine's on, and we can calculate the required ventilation air required. And so we've actually changed that and are installing variable speed drives on those fans underground. And just on the one shop, for example, we'll save half a megawatt hour per year on that. Some of the technical challenges, and as anything else, in some respect, even the technical difficulties are not the only difficulties, right? There are change management and social difficulties to be dealt with as well. So that's a challenge. And then the other one, the mine is really, it's a continual construction site, continually under development. So you need to keep on making changes to your system as effectively your plant changes. And so communication with all stakeholders has been very important. The hierarchical design that I mentioned earlier is very, very important because you can't realistically expect everything to be in good shape all the time. So it's very important that instead of running at a 80% level of efficiency, you can at least, under those times, operate at, say, 50 or 40% level of optimization. I just want to talk a little bit about the technology investment and its effect on sustainable development. And I've tried to show how technology has really been an enabler for projects like ventilation on demand. We have a lot of time of use energy management control strategies in place. For example, mines tend to get wet. You have to dewater them. We automatically dewater our mine only at night, and obviously that's when energy is more available and less expensive. We have some changes in electricity pricing coming up in Ontario called global adjustment, and it really will set us up very well to be able to respond, where basically what global adjustment is, you pay depending on what the rest of Ontario is taking on that day. That really sets your price. And we'll be in a position we can respond very quickly to, depending on what the spot price is at the very moment, we can make decisions about how we want to use energy and what we want to run and what we don't want to run. Our technology has also allowed us to operate a lot of equipment remotely. We've got rock breakers that are all operated from surface. That allows us to run with a low workforce for a start, because you need one person can run any of 6 rock breakers underground, whereas logistically you would have to move someone around to do that. And we can accommodate some of our workers who, for one or other reason, can no longer work underground. It allows us to accommodate those workers as much as possible. And the last just part of the presentation, it allows us to really track not just performance, but also environmental KPIs in real time. And just to talk about this, this is a shot of our operations center. And it's enabled for mobile operator. Okay, so there's a potential for efficiencies, where your operator can now actually multitask. He doesn't have to be in that room to have access to all the systems. He can walk around with a tablet and have access to all the same kind of systems. And it's really designed for status at a glance visualization. And what I mean by that, we spend a lot of effort working on high performance visualization techniques. An example of that there is you don't have to know what any of that stuff is on that screen, but if we tell you we use color and shape to indicate out of conformance conditions, you walk into that room, you have to know nothing. It doesn't matter if you had a bad day or not, you can tell straight away where our issues are in that particular display. Some of the other performance, for inventories, we not only show, if you look at the curves here, we not only show for the last 8 hours, we extrapolate into the next 8 hours. In this particular case here, it's a straight line extrapolation. May not be that useful, but we're working right now on using all the information that we have from our data systems in terms of where movement of material is to actually make a more intelligent extrapolation of all those inventories over the next 8 hours. The display on the bottom here, again, we're looking at our total mine consumption, and given the fact that you have the on-peak and the off-peak pricing regime, it'll tell you how well you're actually doing, and it affects some decisions that the person in the operations center might make as far as starting equipment, operating equipment may be concerned. And lastly, you see on the top right, that's an example of what we want to do with our sump level. Underground, I said, mines tend to be wet. So we really want to let the water in our underground, right at the bottom of the mine, we want to let that rise during the day and pump it out at night. And then, of course, where we want to be is the blue line, and then our actual is traced on the blue line. So very easily you can see whether we're doing well or not. And the bottom left, what we're looking at, these are really real-time environmental intensities, and we report our intensities up through our corporate offices, as all industries do these days. And what we're looking at there is really, this is our power consumption per ton of production, water consumption, natural gas consumption, and we put them in front of the person who is most empowered to make a change now. Okay, we're not looking at these reports last week and deciding what we're going to do next week to make them better. We put this in front of the people who are actually affecting that number, that gas consumption. Before he turns on another burner, he'll actually think about whether he really needs it. And lastly, this is really just a bit about the actual office building that we have there. Spent a lot of effort in making that as environmentally friendly as possible. We have LEED Gold certification on our admin office block, and we realize those kind of savings both in potable water and energy consumption. And the reason why you do this is not only because of those specific savings, but when you work in an environment like this, it makes people think about these kind of things as daily, as a part of everything they do. You know, we automatically turn off lights. We even recover heat out of the shower drains. All right, with that hot water that goes down the shower drain, we recover that heat. And we do it because, not only because of the savings, but because you just create that environment and that culture of conservation and the importance of it. Thank you very much.